So I overheard that you were auditing the class, right?
Yes.
So I'm not sure how many of you are auditing. If you're the only one auditing, you're free to work with the group, not necessarily do the project, but work with all the groups, try to see where they go, kind of stuff, right? So welcome back. So today I want to go off and give a little bit more flavor of some of the different projects out there in a quite nutshell in one lecture before we go to the classes in the textbook from next week. I don't think the textbook gives a context of where these things fit in because it's kind of assumed kind of thing, right? There are a couple of schools which were really big into sensor systems because they got really big grants, right? There's UCLA group, they got $45 million, which in academic terms is a humongous amount of money. And the Berkeley folks, they did the modes and built those little sensors and stuff. So a lot of the work came from them. So obviously the thinking would be what worked for them. So they'll claim that sensors should do what we designed, right? What the hardware should be what we designed, the OS should be what we designed and stuff. So we don't want to be locked into that kind of thinking, right? So the other thing about the course project, I sent an email out of 2 projects, right? See, one of the things is, I think it's nice to build these things, and I like that particular little motherboard because I think it's fairly this big, but it's a 386 class machine, so your regular Linux will run on it and you can do stuff. Obviously, it's slower. I mean, it's 1 gigahertz processor, which you could assume it's slower, right? It doesn't have, I don't think the floating point stuff is not good. But for most normal stuff, it's quite usable. You'll notice it if you try to recompile the kernel, it'll take much longer than your desktop, right? But you can have half a gig or 1 gig of memory. So it's not going to be painful to put that together. So you don't need too much hardware knowledge to put that together. Obviously, you need some hardware stuff. You don't want to fry those things, and it's okay if you fry those. It's just that it takes time to get a new one and stuff. So obviously you can't buy 10 of those just so you can keep frying them, right? So if you do one of those as a project, you'll have to set some parameters of what you want to do. So you cannot say I want infinite budget and it should just sense temperature, because obviously the machine is powerful enough to do interesting stuff. So sensing temperature, it can do without too much hassle. So it has to do something more interesting. Video was one of the things I thought about, storage or something that you can think of, right? And you should set some goal of, the hardware should be $400 or $500 or something that'll help you choose the components, right? And if you come up with the idea, so talk to me if one of those things interest you, then we can do the purchase order and get those components. It takes a little bit of time to get those stuff to you and stuff and things like that. The other project I was talking about was assuming that you just sense something from the machines, sense something like how many users are logged in or whatever. Run those processes and then deal with all the things we'll see in the class. How do you get the contents from all those machines over here, kind of thing, right? Which, if you look at the grid computing folks, they do some of these things, and there's a little bit of overlap and stuff, but essentially that's the thing, right? Obviously, if you have another project in mind that works with the research group, that's good too, right? Does that make sense? So, how many of you actually read the paper? Oh, good. So they were talking. I mean, this obviously, this one group talking about what their project was. So they had their biases. So I put up a slide with a bunch of different groups from a bunch of different people. Took some slides from here and there. So this is the tutorial given at MobiCon, one of the conferences in O2, by Deborah Estrin, who's from UCLA, and she was trying to define what sensors are. So each group is trying to differentiate themselves from other groups. And the Berkeley group was, their claim to fame was that experiment in Maine, where they put the sensors inside the petrol bird burrows. I mean, they burrow under the ground, so they put sensors up there. and they can monitor it from Berkeley campus. UCLA and to extent Berkeley was also trying to monitor local redwood forests, right? So they put sensors around the tree, around the height of the tree, and figure out what the humidity is as you go up. I mean, redwood trees are tall enough that they can notice differences in the humidity and temperature and all those things. And they had these little cables running around with cameras and stuff moving around and stuff, right? And they're also looking at what you would expect from somebody at LA, looking at what earthquakes and stuff do to buildings. So they were working with one of those groups. So, and I like this slide because some of the points that she mentions, it's true across the board. It's not just for them. One which makes it different from sort of the grid kind of scenarios or distributed systems in general is that you expect them to be long-running, untethered, and unattended. You want these sensors to be deployed. Just because the fact that there are so many sensors means that you cannot hope to go back and fix everything. You cannot go back and monitor or fix any of these things. So if you're trying to, let's say, put something around the redwood tree, and I guess they tend to be fairly tall, right, like 150 meters or something. So if you put a sensor every meter or something, it's going to be very annoying for somebody to go back up and change the batteries or fix something, right? Most likely that person is going to be a grad student, right? So obviously none of the grad students or undergrads would want your job in life to keep going every day and replacing the batteries and all those things. And then the next day starts, you change the batteries kind of thing, right? So you want to do something else, right? In that context, it actually makes a lot of sense because, it's like, okay, you can make a system where you have to go monitor everything, or you can graduate, right? Choice is fairly obvious. So you want to do something. You want to have redundancy. All the hardware fails. I mean, there's nothing magical here. Hardware fails for whatever reason. Maybe there's a software bug that you wrote. Maybe there's something wrong with the hardware patterns or whatever. But you fundamentally want to make sure that there's enough redundancy that you can still achieve some performance goals, right? And the other part is what Sean brought up, which is if you have all these things and your goal is to collect all the information back to a central point, right? Then the whole thing would fail. It doesn't scale, right? So even in this case, if all of you have to send me something and you want me to, if I ask some question, all of you send all the raw data back to me, right? One thing is I'll get overwhelmed because I'm getting all this information. The other thing is if your communication worked by routing through your neighbors, people in the back row are happy, the next row are like less happy, and so on and so forth. People who are near me would practically die because they're forwarding all this traffic, right? So you want to use as much of the network itself for computation as possible. And that's one of the nice things about the modern era because the hardware is so inexpensive and cheap and so capable that you ought to be able to do some stuff, right? Now, of course, you want it to be flexible too. So I don't want to be bound to asking only a single question, right? So if you set the stuff to say, what is the room temperature that you're noticing? And if that is one thing I'm getting propagated all the time, I want to be able to reprogram it. So I want some flexibility, and I want to balance it with some processing, right? And they have to be self-configuring, and because if one of those things fail, you should not have to go back and reboot these things, sort of things. So if you set up, so they have to figure out if the goal of all you as a sensor was to talk to me, if I move over to that location, somebody has to figure out something has changed and what should happen and move on, right? And this is what the mobile ad hoc community was talking about for a long time. So they found their calling in this aspect, right? So this is really good. So then you can bring all your expertise into that particular area. And you really don't want centralized control. You want these things to be adaptive. You want these things to make their own decisions and it's kind of evolve into these kind of systems, right? And there's a lot of competing goals with that. So if the hardware is really weak, it's very hard for you to expect a whole lot of stuff from it. And if the hardware is very capable, it can do some of these things, but then you cannot throw a whole bunch of them. So you tend to have a hierarchy. You tend to have some machines which tries to seek another machines. So you have some modes trying to talk to a base station, and so on. And they form a different level. So you have a hierarchy of stuff where some are really incapable and some have more functionality, and so on and so forth, right? So these sort of kind of goals is what you look for, and it sort of defines what a sensor networks are, right? You want it to be self-configuring, you want it to be self-managing, you want some processing being done in the network. You would, and we'll see one other things in the next slide. This is from a different tutorial by Sam Marin at MIT. He's a database person, so the database aspects of it. I'm going to go through the. So the idea here is, once you build, suppose you put all this hardware and they're doing something, they're talking to each other and they do something. What you really want to do is get something out of it. You want to be able to talk to these sensors and do stuff. So the traditional model of programming that you do, that you probably did for your other courses, is you talk to a different application. You have application, you know how many copies there are, you talk to each one of them. The application have to know where all the copies are running and talk to each one of them, right? But in this model, if you have a million of these things, for somebody to keep track of, there's a sensor on that tree, there's a sensor on here, and so on and so forth, is very complicated, especially since most of these machines can die. So somebody has to figure out, go through a loop and say, I know there are a million sensors. I'm going to have to figure out what's the status of each sensor, starting with one, and one might have died. So I have to time out and do kind of stuff. What you really want is a data-centric view, not application-centric view, where you say, I want the data. You guys figure out how you're going to give me and find out the data, right? I want to figure out what's the temperature profile in this room. I want to figure out what's the average temperature in this room. I want to figure out what's the minimum temperature, maximum temperature, so on and so forth. Assuming that each one of you have a sensor, temperature sensor, I want to figure out which part of this room is very hot or which part of this room is very cold, right? So either I can ask that and somehow something happens and I get the response back. So I don't particularly care that this part of the room has no coverage, right? And I care, but there's nothing I can do about it. But I'll get the response for whatever I have. I can also run queries like, if something changes, let me know, right? You guys keep monitoring the temperature, but if there is a hot object and it seems to be moving, then it could be a tank, let me know, right? So there could be some sensors which are monitoring the temperature. They're trying to look for certain characteristics, and some of them are looking for sound, and they find out that if it is hot and if it's moving, hot, depending on what the temperature is, and it's moving, then you got to let me know. Then something has to happen. So the processing happens within the network, but the way I interact is more of these queries and stuff. And obviously, if you're a database person, that sounds like a database, and that's the model that a lot of people like to look at. And incidentally, the mode supports the notion of a tiny DB, where it stores all the. So each sensor would store some of the things that it monitored in its little database, and you send some queries sort of like that. Which says, select the maximum of all magnitude, where magnitude is above a certain threshold, and keep doing this every 64 seconds some time, right? So of all the sensors, you guys figure out what you calculated, see if it's more than a certain threshold, right? And if the number of items which are more than a threshold was a certain number, let me know. Or some, you can change that program. So this is a nice way to interact with these things, not as individual units. So you don't really care what the individual units are. You only care about the semantics of what you want to do, and databases are a good way to do that, right? Obviously, it's not going to be like a regular database. It's sort of a streaming database because the data keeps changing, right? In a typical database, how many of you have taken a course in databases? So if you take a course in databases, one of the things you notice, what's the thing which comes to your mind about databases? What's the one thing that you worry a lot?
Reliability.
Yeah, reliability.
Normalization. Like how consistent your data is.
Yeah, atomic transaction was looking for, right? You look for atomic transaction. You look for some predictable kind of very I think it's all related to what you guys are saying, but atomic transaction kind of stuff, right? So I want to ask for, if I ask for the temperature in this room, right? I want to figure out how many sensors have temperature, are measuring temperature more than 70 degrees, right? I want the answer to be all at the same time, like meaning the measurement to be done at, 2:15:00 across all the stuff, right? In traditional databases, you don't expect the results to come back as he measured the temperature at 2 o'clock, he measured it like noon, and he hadn't done anything after that, and then come back with the answer which is not as precise, right? You cannot expect that kind of accuracy here because these things are resource constraints, so they may or may not be working all the time, right? The response you get, it's not going to be like a database because obviously these are resource constrained, but you still get that flavor, right? So from a database perspective, it's not as good a database, but it gets close to that. And you don't have good information either because the memory is limited, so the old readings might be lost, right? In a database, you don't lose data items, right? The integrity component. You rarely have your database kind of leaking, right? All the old data being deleted. But here, that's the norm. So you have some differences, but the idea. And there's a lot of work done in this context. We'll try to see. We'll try to look at a little bit of those. And one of the ways they call it is geographic information, which we don't typically have, right? Which is, I want to figure out what's the temperature on this side of the room, right? So I can send a query into this sensor network to say, I want the temperature on the south side of the room, or I don't know what side this is, but this side of the room, right? Which means that the query has to go through to somebody. So you have to know where you are, you have to know where the geographic is, and you have to be able to route towards that area, right? So you have to be aware of the geography of where you're sending your queries and stuff, which you typically don't do on networks. You send it to all the people kind of stuff. Here you don't want to bother people on this side because I don't really want this side. It has to go somewhere here. And they talk about geographic routing, and then figure out how to use that. I want to know what's, how the location are correlated and all those things, right? But essentially, these are variations of the database concepts. And he talks a little bit more about what are the aspects of database that you really want. You want to have metadata. You want that data to be tagged with all the stuff like where they are and when they were created and all those things. And it's in network. It's persistent, not as persistent as your traditional databases and stuff. And you want to be able to extend it too, because you want this to be programmable. So you want to be able to add new fields and stuff. And here's the one of the little graphics that they had. So the laptop, which is 0 or something, can send this query and receive all the responses back, right? And this is a big component of all these systems, and that's the component that I said you can do that as a course project using the second one, right? Rather than building sensors which actually measure temperature and stuff, you could measure something about machines. So you still do the same thing. You have to send the query across to all these machines and get the results back, just without having to deal with deploying these stuff, right? How many of you have experience with deploying stuff? I guess you guys did with the team track, right? So what do you do with the team track did you do something beyond the course project, or was it for the course project? Anybody's fine.
No, we did a bunch of exercise, ITA class. So
Okay.
we did a number of experiments, mainly to get some familiarity with deploying this type of system in a controlled environment, and see if we could get a better handle on what kind of sensor data we were going to get, and sort of error rates we would see, and things like that.
Okay.
There was a lot of data collection.
Okay. Yeah. So one of the problems with like real world data collection is you don't want all the sensors to be in single room, right? Because then it's kind of not that interesting. You want things to be kind of spread out, right? So suppose you're measuring temperature, you don't want all to be in the same room because you're going to notice that temperature is the same. But if you have to move outside, then it becomes hard to move around and stuff, right? So if you were to do this as a software artifact, you can just log into a machine, run a program, and it's as good as being all over the place, right? So going back to this paper, this is very old, right? I mean, 2000 is in sensor networking terminology more like, time zero or something, right? The idea was kind of brought out in 99 or so, right? So 2000 is still very early in this stage. So they were building the hardware and stuff. They're defining what those are. So read it in that context. I mean, a lot of the things that, so if you talk to the group now, they change some of the stories because some of the things that they thought they want to do may or may not be true anymore, right? And one of the things is, it's good to talk about like a really, really small machine with like really no capabilities and stuff. But programming that is so hard that at some point people kind of would like to say, wish you can do more than, set the operating system in 178 bytes or whatever, right? Like some very small stuff. So at least the goal at that point was to develop a ultra low power environment, right? And low-cost deployment and stuff. I think the low-cost deployment will always be true for sensors, right? Not without putting a cost to it. It should be low power consuming. It should be low cost. Don't put any value to that number figure like what the paper would say, right? Because in any deployment, you still have to worry about the deployment. For example, the Dream Track helmet, right? Those things may be expensive, but to deploy them is a lot more expensive, right? I mean, since we have captive labor, you can have students walk around with these things, but it's still fairly expensive. You have students wasting their time, walking around and stuff like that. So you want to keep that low. And again, people are trying to, the hardware was catching up with what you can do. So you want to be able to meld the computing with the what the sensors can do, right? Unfortunately, the fonts seem to have mutated from what was in my PC to what was here. So something's kind of went off the board. So one of the things that is true in all these systems to different aspects of this stuff is each sensor you expect it to be doing more than one stuff. You don't want a sensor to be doing only one task. You want it to be doing multiple tasks, right? So for example, if you assume you are all sensors, you may be measuring temperature, you may be measuring humidity, you may be forwarding traffic across the different nodes. So if you want to reach somebody in the back, I may have to forward it through different people and stuff. So each of the sensors in the middle have to do many of these tasks. But the hardware does not let them do all these different tasks at the same time, right? So if you remember from operating system class, most modern machines have these slaves which are helping them. There's a there's a network controller, disk controller, or what have you. So the operating system's job is to schedule something. Say network controller, if you get a packet, do all your processing, and when you're done, just wake me up. I tell you what to do, and then you go on and do the stuff, right? You don't have the luxury here. So you want everything. It's doing a whole bunch of stuff, but it doesn't have enough resources to do all of them simultaneously, even though there's a lot of these things happening all the time, right? So you have to be able to figure out how to process these different stuff while not doing the way that you do in traditional operating system. So one of the ways you do that is to do sort of like a flow through, right? So any task you start and you continue with it till it's finished, right? And hopefully you can switch between different ones, right? So if you're trying to do a sensing, you start the start the temperature, whatever the sensor, measure the temperature, store whatever you have to, and then you finish, and then you move on to the next one, right? If you have a packet coming through, you read the packet, do whatever you have to, and then set it across. So you don't multiplex across different tasks, but you try to do different things on this different one of these things, right? And that changes some of the way you think of operating systems. So if you think of processes or tasks, that's an abstract concept, but when it turns into these machines, it translates into these little threads of operations. Something says, I need to read a packet, do something, forward it, and that may be part of another process or another task from your OS notion, but the mapping is sort of loose, right? from the sensor operating system perspective, all it's doing is it's trying to do each of these little threads. It has to forward something, it has to measure some temperature, all those things. But then there's a larger task, which is you should route, you should respond to these queries and all those things, which is built on top of it, right? And this model of programming, I think it's like a few slides later. People are trying to call this event-based programming, right? And people are trying to push this across to the server-based systems too, and with mixed success. And a lot of people are excited about event-based programming because this is similar to what you do on your GUI desktops, right? When you have a GUI desktop, there's a lot of these events happening. Somebody moves some mouse, and then you have to do some task associated with it, right? So your Windows Win32 API or something lets you say to the something process or something to say, if you see a click, this is the procedure you have to run, and you finish, right? So that's considered event-based programming. So even though you are running a process like Microsoft Word or something, what it's really doing is collecting all these events. It says, okay, if you click, that's an event. You have to go do this particular processing, right? You think of this as a large case statement which says, you do this, this is what you have to do, kind of thing. People took this idea into the sort of the desktops and also to the server, right? If you think of a server, web server, all it's doing is, okay, if it gets an event saying you want a web page, I give it to you. That's an event, right? So you bring that event processing into this model. And it's so hard to program because a lot of people are not used to that model of programming, right? How many of you write Win32, Windows kind of code? Like a truly event-based code, not hello world compiled in Windows, right? What did you do?
I did some of that GUI application.
Okay. So yeah, did you have to do some of this stuff, right?
Right, yeah, database, like GUI application.
So how did you develop that? You use the Windows IDE or?
Yes, yeah, I use Windows IDE.
So if you ever code, you have Windows has a really nice tools, right? Which basically says that if this event happens, you click on something and you say this happens, you write a piece of code and all those things. This is like a joy to program, or it's annoying to program, whichever way. But
I didn't really mind it, but it's very different from C++. Because you have to think of what if someone presses this key or does something over here, does it out of order, you have to kind of control the event flow. So that's kind of interesting.
Well, one of the things which is really annoying to me is you cannot do a program dump, right? You cannot look at the hello world. You can just print the program, and you kind of know what the flow is. But here you can print it, but essentially you're thinking in okay, if this happens, this is the code which gets run, kind of thing, right? And essentially that's what you're trying to do. And if you're trying to do that with 178 bytes of memory, then without any of this GUI stuff, because you don't really have anything, right? It has to do some optimizations because of that, which I think it's the next slide or whatever. Which is, since it does not have enough memory, it has to share some of the resources, right? From an operating system, remember stacks and heaps, right? So stack is the notion that if you're running a process or thread of execution, it has to have this notion of a scratch space called stack, right? Where it keeps this stuff. So if you go to different procedures, you have this stack of execution, right? When you have multiple threads, you tend to have each one have their own stack, so they don't have to fight for the same thing. But since it's not really doing multitasking, so since it's doing each thread by itself, everything shares the same stack, right? Because there's not much space really to give each one a different thread. If you have only a few bytes, you share the same stack. So that you have to be aware that you're sharing the same stack. You cannot store anything on the stack and work, right? And you cannot have heaps, right? Heap is a place where you go and get some memory doing malloc or something. You suddenly need some memory. You go dynamic allocate from a heap. There's not enough memory, so you can't do a dynamic allocation. So you have to know precisely what you allocated, where it's allocated, how much you have. You can't just halfway through say, oh, I need some more bytes. Tough, right? Does that kind of explain what you have to face? So what did you actually do for the?
Oh, I just mostly measured signal strength.
Okay. Yeah, but all the stuff that, if you were to measure the same signal strength on a laptop class machine, right? You have so many tools, and you don't have to worry about all these little details, right? Makes your life a lot easier, but it's not true here, right? So this is from another tutorial where they had the different kinds of modes and what the capabilities are, right? Now, obviously, depending on which group you are, you think that sensors have to be this way, right? Obviously, if I'm the one who's developing this, I would claim that this is the way it should be. And since we're not tied to any of those, you're free to try something else for your course project. Okay. So different modes have different kind of processor with different amounts of memory. I think like the one on the first one has like half a kilobyte of RAM, right? 8 kilobyte of RAM for the programs and stuff. And or on this side, you have a little bit more memory for programs and what have you, right? And they have different levels of battery and different levels of network capabilities and stuff. So even more ideally, what you would really like is write one piece of code and not have to worry about each one of these, right? You would like some sort of abstraction that we are used to, right? Rather than say, I'm writing a piece of code which will work on the Rene platform, right? I would like it to be working on all these platforms, and that makes it even more harder, right? It's hard enough to write for one platform. It's even more harder to say it should work across the different platforms, right? And of course, I mean, they had like nice pictures of the different sensors and stuff. So these are there's a Mica 2 and Mica 2 dot. They started off at Berkeley, and then Intel took over. Intel Labs is manufacturing them and selling them through Crossbow and stuff. They're doing some of the development, partially because Intel wants to partially it's research, and partly because Intel is using all of this in its own manufacturing process. Right? Intel is one of the companies I know is fully invested in sensors across their product manufacturing line. So they want these stuff to be used in their own company, and they also want to use this in other companies as a process control kind of stuff. So they have a certain interest in keeping these things going, right? And of course, there are different. I mean, if you look at different groups, they have different kinds of sensors, and depending on how well heeled you are, you build it differently, right? If you don't have too much money, you buy one of these toys and then put all your things on it. And I think USC had like a small robot. I don't think you can see it, but it's on the size of like a 5-cent coin, right, on the red thing. And apparently this is the Notre Dame one, which I don't think I've seen one, but it's apparently what we built, right? It's not too big if it's not too small. And the other stuff is you can have like a Lego computing pretty much. Right? You can figure out what kind of stuff you want to build these things. You can have different kinds of sensors built into this. So you need to have a common substrate for your computing or something, computing battery and all those things. Then you need to be able to change the battery, the networking module to Wi-Fi, Zigbee, Bluetooth, or whatever you can think of, and the different kind of sensors. And there's some pictures on different kinds of sensors. I think this is the base sensor board. You connect this to your sensor machine, and then you add different sensors. I think it's interface something. So this is supposed to be for light, temperature. The specs over here: temperature, acceleration, magnetometer, microphone, what have you. And these are fairly small like that. So you want to be. So ultimately, when these things work out, you would like these things to be manufactured all in one in nice package and stuff. But for more of research purposes, you kind of mix these things in a sort of like Lego kind of thing. You have this base thing, you put the sensors that you want, and you kind of build a processor. And then you start to program with those, right? And there's a whole bunch of magnetometer and compass and ultrasonic transceiver and stuff. I don't have too much hardware background to know how any of those work, but they look pretty. And there's a motherboard and server board and. Right. So ultimately, you have to figure out, you put this in the environment using these things. You kind of build these little enclosures and stuff, and then you put them out. And you find out that even though you think you know much about how the real world works, you really don't. I mean, there are people who do this for a living, but there are people who are graduate students who build these things, you put them out there, and then you find out that real world is much more wet, much more dry, much more what have you. Right? And we don't have to go through those anymore, at least these groups, because they've been doing this for a few years, right? The first iteration, they build this nice little boxes, and they find out that it does not measure temperature because it's in a nice cocoon, right? And then you find out that if you make little holes, and then the whole thing just corrodes through the hole. So you have to come up with like nice ways to deal with that, right? So, but people like spend like 6 months or something trying to figure out how to actually put them in the environment. It's not as trivial as one imagines, right? Yeah, you find out that the glue that is supposed to be super glue actually does not really hold in the thing. It just peels off and kind of thing, right? Yeah, so those are the different components, like different hardware that you can think of. But there's no reason why we can't do anything else. That's one of the reasons why I think you should try something else, right? And so the team track, when they built the hardware, were any of you involved in the building the hardware part of team track?
Only the extent that we're putting like new sensors on it, like
Okay.
we're trying out a 3-axis compass. I mean, it was a 2-axis compass, but I wasn't involved with anything
Okay.
like that. So to a limited extent, yeah.
But it uses the Stargate, right? Like Stargate kind of stuff for the computation, right? What's the?
I'm not familiar with
Okay. So anyway, so that's the general idea. So you kind of develop these things, but the thing to remember is you want them to be easy to be deployed and all those things to the extent possible, right? So the paper talks more about the tiny OS, and that talks more about the programming that you deal with that. I think I mentioned a little bit of that before the previous slides, right? So essentially, you're trying to use these as the model. You have this like all these concurrent events, and you want to build an operating. So it's called an operating system. TinyOS is considered to be an operating system, but if you took an operating system class, that would not be considered as operating system, right? Because it's doing certain things. It's a set of thread event handlers, collection of thread event handlers, which are each doing its task, right? So you create a set of event handlers, and together you achieve a functionality out of it, right? So when you program it, you just say, if this event happens, this has to happen, and a collection of those together will do good stuff for your machine, right? And the TinyOS maintains a schedule of these things, and not necessarily in a dynamic fashion. It could be static, right? So it's probably more attuned to people who are working in embedded systems rather than traditional operating systems kind of stuff, right? So you can have multiple applications running, but they are really mean multiple threads could be about to run, but only one thread of execution can run, and mostly because the hardware itself does not let you do this different stuff. You cannot let you run 2 different applications at the same time. So that means you don't have to worry about some of the things that you worry about from operating system. You don't have to have locking primitives or any of those things because there's no sharing or there's no protection mechanisms here, right? There's no protection from any of those things. All the threads are supposed to be for the same machine. So inherently, you don't have a notion of protecting yourself from others or protecting from other code. And some of the services it provides, which are fundamental to these things, are the messaging protocols. I mean, it has to be able to talk to do the wireless communication, right? And the reason why it's something that we talk about is the hardware may be so limited that it does not actually know how to do wireless communication, right? It may know how to do the radio frequency communication. To build something on top of it to make it look like a packet may itself happen in software rather than having a network card which does all this stuff, right? In a typical machine, when you buy a laptop machine or something, you get an Ethernet card or wireless card or something, and that does all this processing. Whereas here, you may have to do the modulation. You may have to do, you control the hardware directly in software, so you can actually do a different modulation to the extent that the hardware lets you. You can change the timing or what have you. That means somebody has to do these things. So the TinyOS, you can think of it as more like a library. The TinyOS library gives you calls which makes the radio behave like Bluetooth or what have you. And you need to have a notion of a periodic timer, right? Timing is a very important function in all these things, right? Because timers let these things wake up, right? One of the things is, if these machines were to continuously run, they use enough battery to die out. So they have to go to sleep. So if they have to go to sleep, somebody has to wake up, and they have to precisely know when to wake up, right? That's because if all of them were to coordinate, they all have to be able to say, I'm going to go to sleep, I'm going to wake up in 2 seconds, right? You have to know when the 2 seconds is up. So otherwise, I'll wake up and I do stuff, you're not coordinating with me. So you need to have fairly good notion of a timer. And timing, as we'll see, is also needed for a whole bunch of other stuff, in communication and in terms of running queries and stuff. You need to have a sense of time. And that itself is not a trivial task. Keeping a set of clocks synchronized is not a trivial task. We didn't go through that in the undergrad OS, I know, but at least in the graduate OS class, you might have gone through how to synchronize multiple clocks, right? I think we kind of mentioned it in the undergrad class, but not really, right? So if you remember from the graduate operating system class, right? Did you guys go through synchronizing different clocks, logical clocks, and physical clocks and stuff like that, right? So essentially, the idea here is you have to somehow get all of your clocks into the same, to be synchronized, to be running at the same time. Each one of you have your own little clock, and somebody has to synchronize it, right? So synchronizing would mean that if you assume the relativity theory and all those things, right? You cannot synchronize it absolutely to a time because it will violate relativity properties, right? It can only be synchronized to when you hear it, right? So we can, for example, I can say, if I say something, if you guys all hear it at the same time, that's synchronized, right? Even though she'll probably hear it later than you guys because you're closer, kind of thing. So you need to have this reference to say you're synchronized to that reference, right? You're synchronized to my voice, you're synchronized to something, right? Whereas in the sensor scenario, that's very hard because there's no central, we don't want central anything. We don't want somebody to be sending these pulses and stuff. We have to somehow come up with a way of doing this by ourselves, kind of thing. And that is very complicated. And there's a paper in OSDI, I think, which we may read about it, right? How do you do this without actually having? So you don't want to do unnecessarily somebody pinging saying, this is time 1, time 2, time 3 kind of stuff. In which case it wastes the battery. How do you use it such that when you're doing normal operations, you use that to do synchronization is important, right? Because if you don't do that, then I have no control of where you are, what you guys are doing. So then the whole thing kind of breaks down. So that is considered a part of the underlying operating system. So if you don't have those services, you cannot really do anything. And be able to talk to the hardware devices to do data transfer is a service provided. And some sort of a storage, right? It may just mean main memory, or it may mean like other mechanisms, right? And again, remember that so your hardware may be so rudimentary that refreshing the memory may still be part of your software, right? So if you don't refresh, then the memory may go away, and that services are now part of your software, which you don't think about in the real machine because all those things are taken care by device controller or whatever, right? You may have memory controller which its job is to keep refreshing this memory, whereas here, since it's so weak, it may actually expect that somebody has to do it. If you don't do it, the memory just goes away. And you would like these things to be swapped out in and out on the fly. So you don't want the sensor to forever and ever have this one functionality. You want to be able to upgrade and stuff, right? Many of those things, I don't think we are quite there, right? We can kind of patch them in some sense, but on the field is very hard, right? To give you a sense, I think the largest sensor deployment, at least for the last couple of years, was in Ohio State. I think they had like a very large field where they can put a whole bunch of these sensors out there to collect them, right? I don't remember how many things they had, but I think it's like a very big field that they had out there, but maybe like 100 or so, right? So we don't really have experience in dealing with millions of those kind of things. And depending on the machine, you may have to fit it in very small amount of memory, right? So the three components that they look at is the frame, task, and the command and event handlers, right? Frame is the storage. Storage necessarily does not have to mean like a disk or something. It's somewhere where you can keep something and it'll stay there, right? And tasks are the different things you want to do. You want to say a thing called routing, right, which is part of your task set. But what essentially the hardware does is the event-based programming. So, it knows that if something happens. So if a timer goes off, then it should, some task goes off and forwards a packet or refreshes the memory or what have you, right? And it's very lean multi-threading. I mean, even though it's technically multi-threading, there's only one thread at a time, and that thread has to take an event and finish it to completion, right? So the abstraction, when you talk about it, sounds a lot more powerful than what it really translates to, right? It has a notion of multiple threads, and you do this event registration, but everything is so constrained that the actual implementation is fairly trivial, right? So you can think of this as you're building, you can write this on as a small little case statement kind of program with a severe memory constraint, right? And that's the notion of I actually jumped earlier and talked about the notion of the event-based programming. So everything is event, and you operate on the events. And based on what the event is, you transition from one to another. So based on if the timer goes off, you do certain things, you refresh memory or what have you. And again, like I mentioned, people are looking at this in the larger context of larger systems too, like servers and stuff, right? Actually, I should have waited till I got here, but. So the event-based, so Microsoft was trying to move all its computing towards event-based system, especially for servers, right? Why would you want to do that? Why would you want to invent a new paradigm for like a server, right? Even though it's not related to this class, but in general. Yeah.
Because that's really what the server is doing.
Mm-hmm.
I mean, it gets some kind of input from the network or from wherever.
Mm-hmm.
It does something with that input.
Mm-hmm.
It produces an output, and then it's done with that
Yes.
section.
Yes. You're going to say something?
I was going to say, I think it could provide better response time for network events that you're hardly doing anything rather than responding to stuff.
It's actually a little bit, you can take it a little bit further out, right? Which is, when you think of a server, you rarely have servers running as individuals, right? So you have server cluster, right? So you're really giving an event to this cluster. You don't particularly care who responds back, right? So in some sense, it's behaving like a sensor, right? You don't really care which machine goes down. I just say, here's a URL request. Somebody has to process it, and I give the event to somebody. Some event handler processes it and gives the answer back, right? Yeah. So it does not really matter whether it's running on a HTTP server or what have you. Each event has to be processed by somebody, And thinking of it as events kind of means that I can abstract away all this hardware into this one event and processing kind of stuff, right? So they're trying to develop the theory to see how far they can take that abstraction, where it's no longer machines and processors, but events and the other stuff, right? And so at least in this context, they have to run to completion, right? In the sensor context, if you have an event, it has to run to completion. It cannot be left halfway through. Why would you require that? Yeah.
You're doing with things like radio transmission. We're talking about that you have to receive the data when it's on the radio wire. You can't like hold it. It doesn't have there's no buffer, so it's an immediate need. And switching will just cause you to lose that data.
Yeah, so in general, like the hardware may require you to do some things, right? So if you're starting a radio, you cannot just go away and do something else. You have to continue doing this stuff, right? So in terms of, if you look at a hard disk or something, you have to start it and then you have to keep going, right? Is there another reason you can think of?
There's also only one stack.
Yeah. All the stack is shared. So if you have to swap out, then you have to bring the regular OS concepts. You have to have two stacks. Then somebody has to keep track of which stack was. It has to first figure out where to keep you, right? So you have to, if you want to stop halfway through, remember the OS stuff, right? You have to figure out, you have to create some kind of a table to put you there. You have to save all your states so you can come back. And then I have to go to another one. So I bring in all these tables and stuff, right? We don't want to deal with any of those. So give the stuff, you finish it, and then you're done, right? So does that restrict what you can do with these sensors? That if the model is, you have to complete the task, right? I mean, I guess it's a trick question. Yeah, it does restrict, but I'm saying, does that make some things impossible? Yeah.
It seems like you'd run into problems with synchronizing the clocks on everything then, because say that comes in and it gets put into the bottom of the stack of threads that you have to process. You have to do a bunch of packet transmissions and stuff beforehand. That isn't necessarily going to happen at every node of your network. So you'll have different times if you're trying to do a synchronized reading of some temperatures or something.
So in this context, right, let's not look at a more powerful machine, but like tiny OS kind of thing, right? What happens if the machines go out of synchronization? Like one is doing something, so it forgets to kind of synchronize or whatever, right?
So you could start communicating. You could start sending things over the radio and doing things it's not supposed to, or other machines aren't supposed to.
Yeah, it's practically kind of off on its own, right? Unless they kind of are in some sort of a sync. Yeah, then it's kind of lost. It has to come back to, I mean, once it goes out of synchronization, then it's as good as being lost. And it has to kind of reboot itself or resynchronize itself back to the stuff, right? So some of you are in embedded systems, right? Like at least I know you work in embedded systems and stuff. So for embedded systems folks, this is no big deal, right? Because this is what you've been dealing with in embedded systems all the time, right? If you're playing a DVD movie or something, it has to do certain frame rate for certain stuff, right? If your car is, if you're using this as a car brake or something, you don't want your brakes to be halfway through, stop the braking and go off and, play the music and then come back and do the stuff, right? So this is fairly obvious. So from that community, this was sort of obvious, right? The only difference is, if you're talking about a car and stuff, the way of the synchronization in a car is fairly easy, right? Why would that be? If you have a bunch of components, again here they have to synchronize each other, right? If you apply the brakes, they all have to know when, the different components have to know when they should do what, right? You can't have one tire braking at a different time than the other one. You can have weird stuff, right? Why is that easier? Yeah.
They have a lot of wire connections and
Yeah.
power is really the problem.
So how many of you have any background in like automotive industry? So apparently automobiles have way too many wires, right? They have way too many wires that add too much cost, right? So they're trying to get rid of all the wires and go wireless with the sensor network within the stuff, right? I forget the exact numbers, but the number of sensors in a typical car is like 1,000 or something, and the wires, like this, we have these statistics, right? Like the wires could go from 2 miles worth of wires and all those things, right? Because there's a whole bunch of stuff which are being communicated across the car, right? Not the old rundown car, but like the newer cars with all these sensors, right? Like there's something which is figuring out what the airbag is there, and all those things, right? So they were trying to do this thing because they figured it'll save them a few $100s, right, per car, which could be pure profit if they get rid of all the stuff and put wireless, right? Boeing wants to do that too, because on aircraft, pretty much a whole bunch of these cables go through controlling a whole bunch of things in the aircraft, right? I mean, aircraft has a lot of sensors, checking the temperature and and all those things, and it'll be nice to replace all of those cables with the wireless, right? It'll be interesting though. I don't know if I want to. I would be happy. I mean, I would trust the airlines to fly wireless, right? Especially since they kind of convinced us that if you turn on your cell phone, the whole thing is going to fall out of the sky, right? But so anyway, so when you go into that model, you have to worry about these things, right? So one of the things that they were saying was you would want to get rid of the data cable for if you wanted to go wireless in a car or something. You want to get rid of your data cable, right? But you still want to have a power cable, right? Because you don't want them to be running off of batteries unless somebody wants to change all the stuff. So how do you do this where it's your goal is to get rid of the wires, but you don't want to get rid of the wires by having only one set of wires going in kind of stuff, right? But have enough set of wires and make these things be synchronized and all those things. It's an important challenge, and people are working in different contexts and stuff, right? It's a lot easier than, of course, looking at it from if you deploy this across Afghanistan, how do you keep the time synchronized across all these machines? Right. So one of the part of the stuff that you notice is the migration of what is hardware and what is software, right? And the boundaries are not so well defined as they were in regular machines because the hardware is so weak. So you don't really have a hardware controller. The CPU is the one which is involved with many of these things. And it's also good for researchers because that lets them change the network protocol without knowing exactly what you guys are doing, right? You can probably do a little bit more modulation than what you can do on a regular old laptop, right? Because you're the network card, right? So you can change these parameters and stuff. That means you're putting more load on the processor. Now you have to be careful because if you put more load on the processor, then nothing else can happen. So your machine can, virtually stop functioning and stuff. When it stops doing that, debugging that is nearly impossible, right? I don't know what you're doing, but if you assume that it's also doing some other task, right? If it has to measure temperature or something, right? If they both have to interact with the timing, it's pretty complicated. Right? I had more slides, but so essentially, this should give you a sense of what these different hardware and what these things are talking about. The book actually talks more into the notion of data. How do you deal with data? How do you deal with the communications aspects of it? Right? It doesn't go into the detail of the lower level stuff. So, for example, the idea here is one of the things that before you came to the room, I was talking about was if I put a collection of these the slide printouts, right? If I leave it there, the problem is how do you disseminate it from there to all of you, and how do you disseminate it back from all of you back to the front, right? And that's essentially fundamentally what you have to solve in all these systems, right? You don't want to hard code it. You don't want to say it should go there, but essentially, I need to talk to all the sensors to ask something, right? Which does not mean that I have to physically ask all of them. Somebody has to do the processing, right? So I have to, let's say I'm asking I want to know what is the average age of all the males in the class, right? in this case, I would somehow like the routing to not go to the females without wasting the battery, but still get to all of them, right? So that's the problem I want. How do you disseminate this information, right? And I want to get the results back. So it has to come back from all of you back to me. Yeah, but if you think about it, if it has to come back from all the directions, the first row of people would be kind of dead, right? Because you're doing so much processing. All the queries from me go through you. Everything else comes back to you. But it has to be such that I can go anywhere, should be able to send the information, get the query back, how to do this aggregation, all those things. So the book starts, focuses more of those kind of stuff. But I want to give a sense of what the hardware and software which makes these things possible, right? So how many of you had thought about the course project and what you like to do? Good. What do you have in mind?
Well, we were thinking of a project that would combine both some of the stuff that I would be doing for network
Okay.
and some of the stuff that we're be doing for sensor systems.
Okay. You and her. Okay.
So I'm already working on some protocols for sense networks to like geographic forwarding
Okay.
and dynamic source routing.
Okay.
And I was thinking of looking into some security aspects into that, like some attacks for certain nodes like wormhole attacks or something like that.
Okay.
So is that a good idea?
Sure. But you guys are working on the same project, you said.
No,
Okay.
not yet, but
I thought you said B.
Thinking about it.
Okay. No, yeah, we should talk about it, right, offline. If it makes sense for something else that you're doing, it's always appropriate, right? So the expectations of this class is not as high as what the expectations are for your career projects, right? The expectation of this project, this course project is it has to be something that is tangibly you can show at the end of the class that you've done. It does not have to be a success. Failure is perfectly acceptable, though not acceptable for your papers and all those things, right? So if you try something and you find out that it does not work, that's perfectly fine. But it has to be, so it's not acceptable to say, we were thinking about this project for the whole semester and it's just too complicated. We just can't do anything, right? That means I can't grade stuff. But at first grade, it sounds fine. But we need to talk on how to define what you can do for the class and stuff.
I guess I'll do some literature survey,
Okay.
something like that, and come up with a concrete idea.
Yeah, literature survey alone won't be enough, but yes, it should be fine. But the others, I suggest that people start thinking about something, or else talk to me and stuff. Especially if it needs like purchasing equipment and stuff, right? Notre Dame was a lot faster than other places in terms of buying something, but not. You can't come back and say I need something tomorrow, right? It just cannot happen like that, right? So be kind of early, but do you guys have any questions about? Is it sort of clear on like what this whole thing is about? I hope it's not confusing because I keep going back between the tiny, the mode kind of thing, which I personally kind of hate because it's so low level from what I'm used to that you're forced to you're fairly masochistic on kind of programming those stuff, right? You may have to do that for certain things because of certain reasons, but there's no such reason for this class. So you don't have to kill yourself to run this half of 1 kilobyte kind of stuff, right? So I don't want to teach that as an important aspect. I think event-based programming is important, but the fact that there's only one stack was an artifact of what they have to choose, right? So I hope I make that distinction clear, that even though certain situations may require you to do certain things, the notion of how do you synchronize all these people is very hard, right? Regardless